Hey, we've got Taylor already. Got an early bird. Good going, Taylor. Let's see if there's anybody else.
There's like a
Nope.
contract you can
Taylor, it's just you and me.
Yes, sir. Just us for now.
That's okay. Do you have any questions?
Not yet at this point.
Okay. Now let me adjust this camera here. There we go. Maybe turn this way.
I'm going to be working actually during this class, so I may be like in and out, but I'll be recording it.
That's fine. That's just fine, Taylor. No problem.
Thank you.
I love to have the interaction with you guys because I like to know what you know and what you don't know. Okay.
I think it is very helpful. Yes.
Oh, yeah. Because I don't want to bore you. And I don't want to go over your head either. Well, that looks pretty good. Let's see if anybody else showed up. Nope, just you and me. Taylor, what's the weather like where you are?
It's actually a really beautiful morning. It might be a little
Oh.
cloudy today, but it's still in the 70s forecasted.
Yeah, it's kind of like a springtime. I hear birds out there chirping. Well,
Oh,
I
same
did.
here. Last night I slept with the window open because it only got down to 64.
Yeah, yeah. My wife's got several windows open. It's kind of nice to air the house out.
Oh, yes.
Yeah. My wife said the weather report says there's 20% chance of rain today.
I sure hope not.
Well, I was planning on taking my dog for a walk later, but I guess I could wear a raincoat.
Does your dog have a raincoat?
Well, she's got a coat.
That's true.
Yeah, she's an outside dog. We don't have her in the house. When she was a puppy, we let her come in, but she's very healthy. I think it's more healthy for animals to live outside than inside. But that's just my opinion.
I could see that for sure. I have a dog who grew up with my mother, so he's an inside dog. He's a little one and does not like going outside when it's raining. He like refuses to go outside. Doesn't want to get his paws
Right.
wet.
Well, we have one of those dog glue. Have you ever seen those dog glue dog houses? They look
Oh
like
yes, I know what you're talking about.
they look like an igloo, only they're a dog glue. And
I think we used to have one of those. Yeah.
yeah, it's piled with cedar shavings, and she's just cozy and dry and comfortable in there.
Cedar shavings are definitely the way to go.
Oh yeah. They didn't have any the last time I went to Southern Agriculture, so I got pine shavings, which is not quite as good. What I really
I've never
like,
seen that before.
what I really like is straw. I like straw.
I've never tried that.
Yeah, I just fill the whole house, the doghouse, with straw, and she paws her way in and makes her little nest in there. She's
That sounds really cozy.
Yeah, she's cozy. Well, let's see how we're doing. Oh, in 2 or 3 minutes, we got to get this show on the road. Hey, we've got Ashley with us. Hello, Ashley.
Hello.
Yeah, we got two of us now, three of us. Let's see, there's some homework that's due, I guess, Thursday. And then there's some homework due Saturday, and I want to go over that. I want to beat that homework to death that we're going to do Wednesday. We'll probably spend the whole time today on this problem. I'll go ahead and draw it. It's in your book on page 464. And you know how I like to draw two free body diagrams. So I'm going to draw two of them. Put another one over here. Oh, let's see, we got Shane now. We got another student that just tuned in. Good deal, Shane. I want to talk about this problem. It's on page 464. It's problem 17. Well, the one you're going to do for me Wednesday is 1796. And this distance is 0.25. And this distance here is 0.4. Well, let me look at my class. Oh, it's time for class. And we've got Tyler and Shane, Braxton, Ashley, and Taylor. Good crowd. Now, you don't have to do this homework problem until Wednesday. Today's just Monday. But I want to go over it. I'm not going to do your problem. I'm going to do my own problem. I'm going to change it. But you know the drill. You're supposed to get a red pencil or a red pen, and I've got one right here. And what you do is you put the red stuff on there. Well, let me read this and see what it says. It says 100 kilograms. Well, that means that you've got 981 newtons. That's the weight of this. It's kind of like a yo-yo, really. They're calling it a spool. We have a spool, and the weight is Well, it'd be 100 times 9.81, so it's 981 newtons. And then you have a normal force. Well, that would be 981 newtons also. 981 newtons. We're putting the red stuff on. See, this is the actual forces. And over here, we have the kinetic forces. See, look here, let me put a kinetic force right here. I wonder if anybody knows how to express a kinetic force. Let me just pick on somebody here. Tyler, unmute and say hello, please, Tyler.
Hello.
Yeah, hey, Tyler, this right here is a kinetic force. What do I write for that? Do you know? How do you write down a kinetic force? Tell you what, Tyler, you're hesitating. Go ahead.
Is that your IA?
Oh, that was
Okay.
close. Oh, Tyler, that was so close. You're on the right track. You're on the right track. Here, let me write Newton's second law for you. See, on the left-hand side of Newton's second law, you have that. And on the right-hand side, you have that. Now, Tyler quoted something dealing with this version of Newton's second law. Tyler just quoted that for me, didn't you, Tyler?
Yes, sir.
Yeah, now that's not a kinetic force, that's a kinetic moment. But yes, you must put that on there. And here, let me do it. This thing's rotating like this. So there's your I alpha. There you have it. There's your kinetic moment. But now what do I put here, Tyler? I'll give you a hint. Look at this equation. You figured this one out. What do I put here? Come on, Tyler, you can do this. I believe in you.
Yeah, I'm not too sure on that one.
Okay, now let me go through it here. This is the left-hand side of Newton's second law. This is the right-hand side of Newton's second law. This diagram on the left is the left-hand free body diagram. It has actual forces and actual moments. And this is the kinetic diagram for Newton's second law. It has kinetic forces and kinetic moments. Now that's the kinetic moment, but how do I write the kinetic force for that right-hand free body diagram, Tyler?
Is it the 1/2 mr squared?
No,
Or-
you're in the...
No, that's for the disk.
No, you know what you're doing, Tyler? You're finding the moment of inertia, which is fine. Yeah, no. See, that's what I'm here for, Tyler. I'm here so that you'll get this. See, this is the kinetic force. It's MAG. That's the name of that is a kinetic force. This is the actual forces. Now, I didn't get finished with them. We're going to put them on here. Let me finish putting them on here. Now, your textbook on your homework Wednesday has a force of 50 newtons, but I'm going to do something different. I don't want to do your problem for you. That'll spoil your fun. I'll do something different. Let's do this. Let's have this be 3,000 newtons. It's my problem. I can do anything I want. Now, there's one missing force that I got to put on here, and I picked on Tyler enough. Let's pick on another friend here. Shane, unmute Shane and say hello, please.
Hey.
Yeah. Hey, Shane. There's another force that I didn't put down. Do you
Friction?
know? Do you know what that? What did you say?
Friction?
Yeah. Good going. Good going, Shane. There's a friction force here. We'll just call it F for now. Now here's the thing, Shane. Does that friction force, does it go to the right or does it go to the left? Now, Shane, you got a 50-50 chance of getting this right. Does that friction go to the right or to the left?
To the left?
Too bad. Shane, just stay away from the casino, Shane. It's going to the right. Now what Shane did, he had the friction going to the left. And it actually does go to the left if you want to talk about the force on the road here, or the level, or the ground, or whatever that is. It's going to the left. This what do they call this thing? A spool. This is a spool, and it puts a force going to the left, just like Shane said, on this level surface. But see, what we're doing, when you do the sum of the forces on a body, that's the forces on the body, not on some road someplace, not on some other body, some other place. That's the forces on the body that you're studying. Now, if we're studying the spool, this is the spool, we need the force on the spool. Actually, there is a force going to the left on the road, but there's an equal and opposite force from that the road supplies on the spool. Now they call that, now who was I just talking to? Let's go to Braxton. Braxton, unmute and say hello for me, please.
Hello.
Yeah, hey Braxton. Now Braxton, there's a force of the road on the spool going to the right, and there's a force of the spool on the road going to the left. Now, Braxton, that's Newton's first, second, or third law. Which is it?
I believe that's the third law.
Yeah, good going, Braxton. Newton's third law says for every action, there's an equal and opposite reaction. See, the spool puts a force on the road going to the left, and the road puts a force on the spool going to the right. Newton's third law. Braxton got that right. Okay, we got all the red stuff here. We're all done. We did a great job. We've got the all the red stuff in there. Now let's get this. Let's get the moment of inertia of this thing. Well, there's a moment of inertia about G, and there's a moment of inertia about A. See, this is point A right here. We need to get both of these. Well, if you read the problem, they said the radius of gyration is 0.3. Do you remember that equation? It goes like this. Where this thing here is called the radius of gyration. Okay, so if you have 100 kilograms and the radius of gyration, if you wondered what we're doing, we're studying Newton's second law, and we're looking at a problem 1796 on page 464. That's what we're doing. And they said the radius of gyration is 0.3. So we are going to get the moments about G, and then we're going to get the moments about A. Now I'm going to shut up for a minute, because see, you guys can sit there and be bored and watch me, but it's a little different when you have to figure it out. Have you noticed that? I'm going to be quiet and I want you to get the moment of inertia about G, that's the center of gravity, and then about A, that's the point that it's rolling on. Go for it. Right now, we're trying to find the mass moment of inertia about G and A. Well, I don't know if I gave you enough time, but let me go to one of my excellent students here. Ashley, unmute and say hi, please.
Hello.
Ashley, do you have this moment of inertia about the center of gravity for me?
Is it 9?
That's what I got. What are the units for a mass moment of inertia?
Kilogram meter squared?
You got it. Jolly good. Ashley, did you get the moment of inertia about A?
Is it 25?
That's what I got. Now, I'll be glad to go through that if anyone asks. I'm listening now. Somebody asks, somebody say, please do it, Mr. Griffin, and I'll do it. I'm listening. Well, I just assume that you can do it. You have to use the parallel axis theorem. Okay, great. We got that done. Now, what are we supposed to do anyway? Let me think about this. Oh, well, why don't we we have this normal. The normal force is 981, but we don't have the friction. That'd be fun to find the friction, wouldn't it? We'll try to find it. Hey, here's something else. Oh, we just got this. Look here. Well, we don't have the alpha. There's some stuff we don't have here, folks. We don't have the alpha. We don't have the linear acceleration, AG, and we don't have the friction. So we got to find all those. We can do that. Let's do this equation. But by the way, this equation has a name. See this one right here that I'm looking at? The sum of the moments about G is equal to IG alpha. That equation has a name. Let me ask, well, we don't have that many students today. I wonder where everybody is. Tyler, let me pick on you again. You're a good sport. Tyler, unmute and say hi, please. Earth calling Tyler. Come in, Tyler. Uh-oh, Tyler said that he was in and out. Let's get somebody else. Let's see here. Oops, wrong one. Taylor's with me. Taylor, unmute and say hi. Uh-oh, coffee break. One more try and then I'll give up. Shane, unmute and say hi for me, please.
Hey.
There you go. Shane, you see this equation that says sum of the moments about G equals IG alpha. That equation has a name. Shane, what's the name of that equation?
I don't know the exact name. Is it the mass moment of inertia?
No,
Is it?
that's Shane. That equation is called Newton's second law
Oh, okay. Okay.
for rotation. Now,
Gotcha.
if I'd ask you this one, Shane, you'd recognize that. That's Newton's second law for translation. But see,
Gotcha.
this is Newton's second law for rotation. Okay, well, let's do it. Here goes. Some of the moments about G. Well, I wonder if you could write that. You're going to have to go 3,000. You're going to go 3,000 newtons times 0.25 meters, plus or minus. Well, it's clockwise, so that'd be minus, plus the friction times 0.4 meters equals 9 kilogram meters squared times alpha. I just wrote this equation here. See it? Uh-oh, it's got two unknowns. Well, I'll tell you what, let's write this equation. Now that equation there will be 3,000 plus the friction equals the mass times acceleration. Ah, dang. Well, we got three unknowns now. See, we don't know F, we don't know alpha, and we don't know A. But we have a third equation. The third equation is equal to A equals R alpha. Now that is if it's rolling. If it's rolling, the acceleration of the center of gravity is equal to that R, which is 0.4 times alpha. And so you can put that in here. You can get rid of that and write that as 100 times 0.4 alpha. And now we have two equations and we have two unknowns, the alpha and the friction. You see that? And we can solve it. It can be solved. I'm going to shut up now, and I'm going to let you do some algebra for me. But first, is there any question about what I did? All I did was write these two equations down. Any questions from anybody on how I got those equations? And now just a minute, it might be wrong. Let me look at this. We did this counterclockwise being positive, didn't we? Yeah, and so clockwise is negative. But see, the alpha is a negative. So you either need to put a negative here. You're going to get wrong answers if you do this, guys. You're going to need to make this plus and make this minus. See, what I'm doing here is I'm writing this clockwise as being positive, and this is counterclockwise, so it's negative, but this is clockwise, so it's positive. I just decided clockwise was positive. The way I had it, you'll never get the right answer. It can be tricky, but I think now we have the right equations. This one's okay. I'm going to shut up now for a minute and a half. I don't know if that's enough time for you to do the algebra, but I'm going to see if I can do it in a minute and a half. If I can do it, you can do it. You're as good with algebra as I am, probably better. Okay, go for it. Find the friction and the angular acceleration of that spool. while I try to do the same thing. Well, I got some answers here. I wonder if they're right. Did anybody get, when they tried to solve these equations, did anybody get an alpha of 78 and a friction of 120? If you did, say, uh-huh.
Uh-huh.
Yeah, there's two of us.
Uh-huh.
Yeah, there's three of us. How about another uh-huh? Okay, well, there's at least three of us. I bet we did that right. We found the friction. It turns out to be 120 newtons going to the right. And we found the, hey, we never did get the acceleration, the linear acceleration. Let's get it. See what that is 0.4 meters times alpha. Well, I can do that. Let me try that. 0.4 meters times alpha. 4 times 78. I'm getting the acceleration of the center of mass is 31.2 meters a second squared. How about you? If you got that, say, That's not what I got when I did this before. Must have goofed up. No, wait a minute. Something bad happened here. No, wait a minute. No, that's right. That's what I got when I did it before. Everything's okay. So look, we solved for the acceleration. We solved for the angular acceleration. We solved for the friction. We did great. But there's an easier way. Let me write Newton's second law in the other forms. You know, there's three forms of the rotational version of Newton's second law. Do I have room here? Maybe. One of them goes like this. And one of them goes like this. There are three rotational versions of Newton's second law. This is Newton's second law for rotation, but it comes in three different forms. And here they are. Now, this third one is really a winner because if you're rolling, this term here drops out if you're rolling, because there is no horizontal acceleration of point A on your wheel relative to your flat surface because it's rolling. There's no slipping and there's no sliding. See, if there's any slipping or sliding, then you have a term here that you have to include. But if it's rolling, the acceleration of that point A on the wheel horizontally is zero relative to the road because it's not slipping and it's not sliding. See, sliding is when you put on the brakes and leave skid marks. Slipping is when you mash your acceleration, your accelerator, and you're burning rubber. But you have an acceleration relative to the road in slipping and sliding. Here you're rolling. So this term drops out, and you've got a beautiful equation that works if you're rolling, or if you have a fixed pivot, or an ICZV. So let's do that together. Let me make a little room here. I trust you've written down these moments of inertia. Here's this beautiful equation. It says the sum of the moments about A is just equal to IA alpha. Now be careful with this equation. It only works for rolling. But we are rolling. Now you'll find that equation in your book. Let me show it to you. Someplace in here they'll have that equation. There it is. It's, well, that's not exactly what I wanted. Let me keep looking. There it is. It's on page 442. This equation is on page 442. It says the sum of the moments. Now they put O there. Instead of having an A, they put an O there, okay? It's just a dummy variable. It's that point about which it's rolling. And so they have an O right there. We have an A on ours. But that's the equation for a fixed pivot or for a rolling spool like ours. And this is so much easier to work. Let's do it. Here goes. Some of the moments about A, well, the friction doesn't give you a moment because it goes through A. The normal doesn't give you a moment, it goes through A. This weight of 981 newtons doesn't give you a moment because it goes through A. The only thing that gives you a moment is the 3,000 newtons times, well, in this case, it'd be 0.65 meters. Do I need to explain the 0.65 meters? Do I need to explain the 0.65 meters? See, that's the distance from A up to the line of action of your 3,000 newtons. You go 0.4 meters, 0.25. If you add them, if you take 0.4 and your 0.25 and you add them, I get 0.65. Okay, now this is a clockwise moment, and it's equal to IA, which is, one of my excellent students told me it's 25 kilogram meter squared times alpha. Look how nice that equation is. Put that in your calculator and tell me what you get. Go ahead. Boy, Juve. When I put that in my calculator, I got 78 radians per second squared. That's the answer we got doing it the hard way. Ooh, that's a nice little equation there, isn't it? But you got to be careful. Let me put a little skull and crossbones on this equation here. You got to be careful about it. You can't always use that equation. It only works for fixed pivot, for rolling in this case, where you've got this instantaneous center of zero velocity. Did you know that every portion on that spool at that instant is rotating about A? Well, there's your alpha. Wasn't that a lot easier to get than having to solve these two simultaneous linear equations? Now, once you get alpha, then you can use I got lost here. Once you get alpha, you can get the acceleration. And once you have the acceleration, you can figure out your forces. Any questions on that? Wasn't that fun? Now you're doing one just like it, only this is different. I've changed this to 3,000, and the one you're going to do is 50. Yeah, your problem has 50 here. So you're going to get different answers. Any questions from anybody on that one? Okay, well, let's do a different one. I need some room to work, so I'm going to sacrifice some of this stuff. I don't think the normal is going to change any. We'll get a different friction though on this new problem I'm going to give you. We'll erase that because our numbers are going to change. Now here's what I'm going to do. Now these equations are still good. But on this one, I'm not sure you're going to be able to cross this one out. We might have to, that might be a keeper. You only get to cross it out if you're rolling, we're going to make this 5,000. Make this force 5,000 newtons. Okay. Now we're going to write our equations. Here we go. Let's write this equation here. Well, what do we got in the x direction? Well, we got 5,000. But we also have the friction. It's in the x direction. And the total is equal to the mass times the acceleration of the center of gravity. I have just written Newton's second law for translation. Okay, now let's do, let's assume it's rolling. Let's assume it's rolling. And if it is rolling, hope you can read my writing. If it is rolling, then we can use this equation here. Remember, that equation only works if it's rolling. We're going to find out if it's rolling or not, and we're going to write the equation. Here we go. Sum of the moments about A. Well, that's going to be 5,000 times 0.65. If you don't know where I got the 0.65, just speak up. Don't be embarrassed. Just say, Mr. Griffin, where'd you get the 0.65? And I'll explain it again if you want me to. Okay, nobody, I didn't hear anybody, so I guess you understand it. Now that's clockwise. There are no other moments about A because all the other forces go through A. So that's going to equal your 25 times alpha. If it's rolling, this term here drops out, remember, because the point A on your spool doesn't have any horizontal acceleration with respect to your horizontal surface. Okay, solve that, and let's see what we get for alpha. Go ahead, I'll shut up. You solve that, get that alpha for me. And I'll ask somebody. I want to see if anybody's still awake out there. Let me go to my friend Ashley. Ashley won't let me down. Ashley, what'd you get for alpha, the angular acceleration? What'd you get?
130
That's
radians per second squared.
That's what I got. 130 radians per second squared. Okay. Well, now we can get the translational acceleration of the center of gravity. And you need to know something about that equation. That equation has a skull and crossbones on it too. That equation only works for rolling. It works good if you're rolling. The translational acceleration is equal to r times alpha. But see, if you're not rolling, that equation doesn't work. But we assumed it's rolling, and so we're going to do it. And if you do that, it'd be 0.4 times your 130, and you will get, I'm getting 52 meters per second squared. So we have the linear acceleration of the center of mass if we're rolling. Now we're going to use Newton's second law, this one here, the translational version. We're going to take the sum of the forces in the x direction, which are 5,000 minus the friction. No, plus the friction. I just about goofed up. Plus the friction equals 100 kilograms times 52 meters a second squared. Now we're going to find the friction. Go ahead and plug that in and get me the friction, please. Hey, I can do that in my head. Did you guys get 200 newtons for the friction? If it's rolling, that friction's got to be 200 newtons. I need to hear an uh-huh.
Uh-huh.
Yeah, I think I heard an uh-huh. I need another uh-huh.
Uh-huh.
Yeah, that's right. Now here's the thing. We're going to test and see if we can get that kind of friction. There, in the problem, we're doing problem 1796. Only we changed it because I didn't want to do your problem. You're going to do your problem. I changed it. But if you read that, they said the coefficient of static friction is 0.2. What that means is the static friction is less than or equal to 0.2 times the normal. Okay. Well, the normal is 981 newtons. What's 0.2 times 981 newtons? Let's find out. 0.2 times 981. I'm getting 196.2 newtons. You know what? That's as big as the static friction can ever get. It can never get to 200 newtons. We don't have 200 newtons. You know what we're doing? We're slipping. This wheel is turning too fast because we've stepped on the gas here. See that 5,000 newtons? This thing is spinning, it's laying rubber. It is not rolling. Friction can't be 200, like we said. It can't be. You can't get that high. See, static friction has a limit. The biggest you can ever get is 0.2 times the normal. Well, that's 196. For this thing to roll, we got to have 200. So it's not rolling, it's slipping. Well, if it's slipping, you can't use this equation anymore. It's really not an equation, it's an inequality. But you can use the kinetic friction, which is equal to mu sub k times the normal. Now, if you read the problem, the mu sub k is 0.15. So it's 0.15 times your 981. And we can get the friction. It won't be 200 though. It will be 0.15 times 981, 147.15. Friction is 147.15 newtons. That's what the friction is, 147.15. Well, that kind of changes things. Going back to this first, the Newton's second law, we're going to have to rewrite that. Where did that go? Here it is. You got 5,000 going to the right, but this is no longer 200. This is 147.15. Here, let me put that in. Friction is 147.15. 147.15. 5,000 going to the right. 147.15 going to the right equals 100 kilograms times the acceleration of g. Now I want you to find the acceleration of g for me. Did you get the acceleration of g is 51.4715 meters a second squared. It's not 52 anymore. This equation doesn't work anymore. Remember, it had a skull and crossbones. Now, did we ever get the alpha? We got the friction. I don't think the alpha is a 130 anymore. Let's get the alpha. I need some room to do that. Here, let me make some room. We don't need this stuff. It's all in your. It's all on Blackboard. You can look it up. To get the alpha, we're going to have to go to this equation here. Sum of the moments about g. That's going to equal to Ig alpha. What do we got about g? Well, we have 5,000 times the 0.25. That's clockwise. And then we have minus the 147.15 newtons times the 0.4 equals, we're doing this equation now. Ig, didn't we say that was 9? Yeah. So we can get our alpha. Here we go. We're going to find alpha. Remember before we got 130? Well, I don't think it's 130. In fact, I think it's bigger maybe. Let's find out. Put all that in there and let's see what happens. You know what? I got an alpha of 132.349 radians per second squared. You know what? It's spinning too fast. To roll, you need to have 130. But this alpha is 132. It's somebody stepped on the gas. And they're laying rubber. And the alpha is too big. But that is the alpha. If you put 5,000 newtons on here, there's the alpha. And the friction is not 200. It's 196.2. No. I'm getting mixed up now. It's not 196.2. It is 147.15. Let's write down the stuff. The friction is 147.15. The alpha is 132. Now, if you tried to go, well, yeah, and let's get the acceleration of g while we're at it. It's 51.4715. So we know everything. We know the friction. We know the acceleration, the linear acceleration. We know alpha. But if you tried to write AG equals R alpha, that won't work here. You might try it. See, R is 0.4. Take 0.4 times this alpha, and let's see what we get. You don't get that. I'm sorry. You know, this only works if you're rolling. And we're not rolling, but we still were able to find the linear and rotational velocities, or I mean accelerations, and the friction using Newton's laws. Now there's a third law. I never did use it. Why do we use it? That's this one here, only you don't throw this term out anymore. In order to use that, I need some room. So let's make some room. Here we go. I'm going to make some room. Let's stop and give a repeat of the basics here. There are 3 rotational versions of Newton's second law, and here they are. There's that one. And then there's this one here. These are really all vector equations. And then there's a third one that goes like this. There they are. There's 3 versions for Newton's second law for rotation. There's only one version. Well, if you write it in components, you could write different versions. It's scalar. You could write the scalar components and the x and the y. And even in the z, if you're in 3 dimensions. So you could write 3 versions, not that one, this one here. You could write 3 versions of Newton's second law for translation, just in the x, y, and z directions. But I think we already all knew that. But these are the 3 in the y direction. Now we've done these 2, or have we? We've done this one. I don't know if we've done these 2. Well, let's do them. Here we go. We are going to try plugging in these 2 equations and see if they work. This is called checking our work. I know we can do this. Okay. Let's do this one. Here we go. I need the room. All right, we'll make some room. Here we go. Notice I erased that first one because we've done it. But I don't know if we've done that one. Let's do it. Some of the moments about A. Well, there's 5,000 newtons times 0.65 meters, right? Clockwise? Yeah. Equals IG, which we decided was 9, times alpha, plus R. Well, R goes from, if you're doing it about point A, you go from point A up to G, that's 0.4. The mass is 100. And you can solve for AG. Okay. Plug all this into your, wait a minute. We got two unknowns here. We got the alpha, we did that, it's 130. So let's just put that in there. Now that'd be 9 times 130 plus, well, solve this for the acceleration of your center of mass and let's see what you get. Okay, I'm doing it. Okay, something bad happened. Just a minute here. This is wrong. The alpha is not 130. The alpha is 132. Let me put in the right number here. It's 132.349. So let's put in the right number and let's see what we get. Go for it. Well, boy, Juve. When I plugged that in, I got an acceleration of G of 51.4715. Well, that's the answer. We know that's right. But I don't think we got it with this equation. I think we got it using this equation here. But it checked out. It's called checking your work. That checked out. Now let's check out this one. Is there any question yet? Gee, I don't know. I got a bad feeling like maybe some of you got lost someplace. I hope not. What we're doing is we're taking this problem you're going to do for me Wednesday, 1796, and I changed it. And I put 5,000 newtons on there, other than what they had in the book for their problem that you're going to do. I changed it. We solved it, and we got all the answers. There they are. And we're just checking it to see if it works. It works with this problem here, or this equation here, because that's how we got those answers. It works with this equation here. This is another version of Newton's second law for rotation, but we haven't used this equation here. Let's do it, shall we? That'd be fun. Unless there's a question, we're going to do this. We're going to find the answers and see if they fit. We're checking our work for this equation here, which is another version of Newton's second law for rotation. Any questions? Well, okay. Here we go. Some of the moments about A. Well, we just did that. The sum of the moments about A are 5,000 newtons times 0.65 meters. How come these other forces don't give you a moment? I'm going to ask somebody. I want to make sure you guys are with me. Shane, how about it, Shane? Can you unmute and say hi for me, please, Shane?
Hi.
Yeah. Now, Shane, these red forces here don't give a moment about point A. How come?
Because they go through A.
Yeah, he knows. He knows. I was just checking up on you, Shane. Proud of you. He knows exactly. He knows. If a force goes through a point, it doesn't give you any moment about that point. We all know that. The only force that gives you a moment is this 5,000, and it's 5,000 times that distance, which is 0.65 from A up to that 5,000. Okay, but we're writing this equation here now, so I need to erase this stuff. And I need to put in the 25 kilogram meters squared. Because see, that's the moment of inertia about A times alpha plus R. Now R, we're doing moments about A, so you go from A up to G, which is 0.4, times the mass. The mass is 100 kilogram. And here is the acceleration of A. Now the acceleration of A, we can't plug in alpha R anymore. Do you understand? Because, well, we don't know what the acceleration of A is, but we're going to find out. Let's talk about the acceleration of A. There's the equation. I think we wrote it right. Now we know what the acceleration is. See it? We figured it out two different ways. So we could find that acceleration of A. But let me show you how we can do it. I got a little room right here, not much. There's some room in here. Let me make some more room in here. Yeah, there's some room. There's my equation. We're trying to find this acceleration of A. Now, see if you can follow this. We're going to talk about the acceleration of A relative to G. If you lived at G and you're an observer there and you're looking at A, A appears to be rotating clockwise, you know it? It sure does. Acceleration of A relative to G. It appears to be going alpha times 0.4. Here, let me write it this way, though, just a minute. By definition, this is called relative velocity. The relative velocity of A relative to G is not velocity. This is called relative acceleration. The relative acceleration of A relative to G is acceleration of A minus the acceleration of G. Yeah, okay. By definition, really. We studied relative acceleration a while back. I don't know if you remember. And see, this is what we want. See the acceleration of A right there? That's what we want to put in here to check this problem. We can solve for the alpha. We already know what the alpha is. We've done it twice. Okay. Now we know what the acceleration of G is. We've done that. So we could plug that in. Now, here's the thing. The acceleration of A relative to G is equal to alpha times 0.4. So as far as G is concerned, A is spinning about G. And it has an angular acceleration of 132 point blah, blah, blah. So we can write that as 132.349 times 0.4 meters equals, we're trying to find the acceleration of A minus, now the acceleration of G, we know, we've done that, is 51.4715. Can you guys see from this we can get the acceleration of A? I think we can. Yeah, okay, plug it in and get the acceleration of A, go for it. Now, wait a minute, I'm getting mixed up here, just a minute. This might need to be a minus. Yeah, I think it is a minus. See, positive acceleration is going to the right. There's a minus here, but the acceleration, this is a positive 51. It's going to the right. But this acceleration of A relative to G, it's spinning clockwise, so it appears to be going to the left. It's negative. So put a negative right there and solve for acceleration of A. Here we go. Well, I got an answer. When I solved this, I got the acceleration of A to be a negative . Well, what does that mean? Well, it means it's the thing's spinning clockwise, and because somebody stepped on the gas, and acceleration of A is to the left. So we're going to have to put that in right here. So that's a minus. If you take that and plug it in right here, we're going to solve for alpha and see what we get. And it better be this here, because we're checking our work. We're seeing if this equation works. Well, okay, here we go. And now this is a clockwise, and that's clockwise. And this would be clockwise also, yeah. Wouldn't it? Let me think now. See, R is going this way, and A is going this way. And when you cross R into A, wait a minute. R is going from A up to G, and A is going to the left. This is a little bit complicated. And when you cross those, you don't get clockwise, you get counterclockwise. So this is going to be, it'll be a minus, but that's what you'll get when you plug in that minus. Yeah, okay, plug it in. Let's see what happens. Here goes. Plug in this equation where A is given by this right here. Let's see what happens. Boy, Jove, when I plug that into right here, I get an acceleration of 132.349 radians per second squared. Check. Well, really a double check, or maybe a triple check. All three equations, this one here, and this one here, they all say the same thing and give you the same answer. I bet you can do that problem now. That one was a little bit tricky, that last part. Did anyone have any questions about that? Well, we worked that problem 1796 to death. And we have a few minutes, and I want to talk to you about where we're headed next week. We'll be meeting again this Wednesday. And you'll be given a exam 3 on Wednesday. It'll be available. And it'll be due Saturday. I think I wrote that down at the beginning of class, but it's in the syllabus, or it's in the Blackboard. You can read it. But let me tell you where we're headed. Now, this will not be on the test, but we're going to talk to you about energy, kinetic energy of rotation. I'm going to make some room here, and I've got a few minutes left, and I'm going to talk to you now about kinetic energy of rotation. And Wednesday, when we meet, we can have more review. I can answer your questions. You're going to have your test and some homework to do. And then I would like to spend some time on kinetic energy. Now, there's two kinds. There's kinetic energy of translation, and there's kinetic energy of rotation. You all know this one. It's 1/2 mv squared. But you might not be that familiar with this one, and we'll show you where this comes from, probably Wednesday. But it's not 1/2 the mass times the linear velocity squared. It's 1/2 the mass moment of inertia times the angular velocity squared. And we'll try to show you where that came from. You need to know, though, that the book again has their own little secret nomenclature. They don't say kinetic energy. They say T. That's their secret symbol for kinetic energy. So when you read this chapter 18 and you see a T, I like KE personally. I don't like T, but I can't help it. That's the way the book does it. Now, they also have a symbol for work. Their symbol for work is a U. I don't like that either. I've shown you this before. But we'll show you again. See, if I was doing this, if I was writing this book, I would go KE as kinetic energy. And for work, I would go W. Doesn't that make more sense? W is work, but I can't help it. They use a W, not a W, U. They use a U. And finally, for potential energy, if I was writing this book, the way I would write potential energy would be PE. I know what that is when I see it. That's potential energy. Well, they don't use PE either. If you flip through this chapter here, where they got this symbol, I don't know. It's a pretty good book otherwise. How do you spell potential energy? Is it TIAL? Their secret symbol for potential energy is a V. If you read the chapter, you'll see that. So read ahead. We'll get to that chapter on energy soon, but it's not on your test. But we're going to have to learn it. Okay, we've had some fun, I hope. We tried a problem using Newton's second law a bunch of different ways, huh? Do you have any last words or comments? Well, okay, if you don't have anything, I'm going to push this little red button here in a minute. You sure you don't want to say anything? All right. Well, bye-bye, students. I'll see you Wednesday at 9:30.
Bye.
Bye-bye.
See ya.
Bye-bye. See ya.